All right, so start a little bit early here. Guess the weather's too nice for anybody to show up. So I can't stress enough. I mean, you guys can do whatever you want. I probably shouldn't be talking to you, I should be talking to people who aren't here. But it's going to be very important, especially the next 2 weeks when we're covering like regression stuff. I don't think you're going to get it as much unless you're seeing things worked out in class. You can ask questions. So where we're going to go, kind of going a roadmap. I've first of all, I want to mention I've kind of uploaded the kind of latest iClicker scores onto Canvas. You should after today. I'm going to change up, I think, a little bit from what I said Monday, which is that we're going to do Excel primarily on Friday. So I'll post the next Excel assignment when I get back from the office this afternoon. You could probably piece together, like work through some of it based off what we've already talked about, working through it by hand and one population examples. But we'll go through all the 2 population examples in Excel on Friday. Okay? Now, I want to mention that 4th Excel assignment will be due that Friday before exam week. I'm also going to have 1 more Connect and 1 more Excel assignment. So you're going to have kind of congruent Excel assignments. The 5th one, really you'll have everything you need to complete it after next week. So you'll have kind of that last week to work on that 5th one. But here's kind of the caveat. If you've done the first 4 Excel or you've done the first 4 Connect, and I drop the lowest score, what could you do? Not do the last one, right? It's a 0, it gets dropped. So if you do the first 4 Connect, first 4 Excel, and you're pretty comfortable with what your grade, your grade there is, you can not do the 5th one and it wouldn't change, right? I'll drop that lowest score. Okay. And now if you've missed one already, you should definitely do the remaining ones, right? Because you've got a 0 sitting there, and if you get 2 zeros, well, one of them is going to count, right? Any questions on this kind of, I guess, class stuff? We can jump into material here today. Okay. So we talked last class about, I think we ended it with we did confidence intervals for the difference in sample means, and I showed you what the test statistic looks like if we do hypothesis testing for situations where we have only sample variances, right? And we said it really looks identical to what we were doing when we had known population variances. It's just that we use sample variances, so we have to use that student t-distribution. That was the only thing really different. Okay? So all the steps are exactly the same. And we had this idea of the degrees of freedom equation is going to be a little bit nastier, but I said, I'm not going to make you guys do this. I will give you what that value should be. And so that makes life a little easier. Okay? So this is going to be our test statistic equation. This is how we find our degrees of freedom. So let's work through an example. So we want to know whether or not male and female salaries, physician salaries are different, right? So we take 41 male, 41 females, we find the sample mean for both groups, and we also calculate the sample variance. Okay? Really, to find what our null alternative hypothesis are. So our alternative is what we want to test for. So we want to know, is male starting salaries different than female starting salaries? So anytime I see this term different than, what should I be thinking about for my alternative hypothesis? A not equal to sign, right? Same thing applies to 2 population examples as 1, right? And we're just saying, are they different than each other? We're saying that if I take the difference between male and female salaries, is it anything other than the value of 0? Because if it is, that means those 2 values are different, right? If it was equal to 0, that would mean they're exactly the same number, right? Or that male and female salaries are exactly the same. So what we're trying to test for is whether or not that difference is something other than 0. We'll assume the opposite is true, which is that it's equal to 0. So hopefully, I've tried to mention this a lot. You see something that's like on the exam. I said that I'm always going to give you an assumed true difference of what for these 2 population examples? 0, right? So, I mean, we should be looking at kind of the sample difference. I looked at some of the other iClicker scores when I asked this question, the previous one. You're not using your sample difference here as the assumed true value. The sample difference is what you're trying to use to say, is what I assume to be true or not, right? Is the sample evidence kind of go against what I assume to be true? So here, we're always going to use this assumed true difference of 0. So we've got a 2-tailed test. Next step might be, well, let's find our critical value, okay? So We could calculate the test statistic right away. It doesn't really matter what step, what order you do these steps in. It's sometimes just easier if we're going to do the critical value approach, plot my critical value, draw the rejection region, then plot my test statistic. So here, if I want the 1% significance level, what's my alpha value? Yeah, 0.01. But if I've got a two-tailed test, the cutoff number of standard deviations away I need to go, well, evidence on either side goes against the null. So I'm actually going to have a pair of critical values. So alpha total is in my tails now, which means this looks very similar to confidence intervals, where I take alpha and divide it by 2 to figure out, well, what's the area in each tail? Okay. So I've got 0.005 is the area that I want in that tail. I've got a student t distribution. These critical values are going to be the cutoff number of standard deviations away, right? That if I see sample evidence that's any further than that, I'm okay rejecting the null. But they're coming from now, instead of a standard normal, student t distribution. Okay. So what else do I need for my student t distribution? Freedom. Yeah, and you know which one am I using, right? All those rows of the table, different degrees of freedom. So here I told you, and I use delta to kind of notate our degrees of freedom when we have to use this equation. So we've got a degrees of freedom of 80. Okay. So we're going to go to our t table. We want 0.005 in the tail. We got to scroll all the way down to a degrees of freedom of 80. So 2.639. Right? So 2.639, positive and negative. Often we'll write this kind of like that, right? So it identifies that for a two-tailed test, I have two critical values. For a right tail or left tail test, I have a critical value, right? So one tail test, you have one critical value. Two tail test, you got two critical values. I think that's not too terrible to remember. So here's our rejection region. The next step is, well, what's my test statistic, right? So this is going to be a little bit of an extreme example, so I'll walk through this here. All I do at this point, you're going to have, you have these formulas in front of you. Like I said, the formula sheet for the final is up there on Canvas already. If you're wanting to use that when you're working on homework, so that might be a good kind of thing to do. So you'll have this in front of you. We assume the difference is 0. It's just a matter of plugging in the information we're given. 174,000 for males, 141,000 for females. So the average difference we found was what? 33,000. So right away, I know my test statistic. Which of these can I rule out? The negative ones, yeah. So if you think about, if I've assumed that true difference, sorry, I'm jumping ahead. If I've assumed that true difference is 0, right? And I found what, 33,000, right? Was that kind of sample difference? I'm a certain number of standard deviations above that assumed true value, right? So it kind of makes it easy with these two population examples, because we're always using this assumed true difference of 0. If I find a positive sample difference, well, standard deviations are always positive. So positive over a positive, I'm going to be a certain number of standard deviations above. If I ever find a sample difference that's negative, well, negative over a positive, always going to be a negative value, or a number of standard deviations below. Okay. So from here, it's just a matter of I have to work this out, right? Now, which of these seems like maybe between the two positive values, which one probably seems a little more unlikely to be the test? Yeah. So there's a good point. I made this example to prove this one. So probably on the exam, I wouldn't give you an example where you get a test statistic this large. But if we're looking at the sample evidence we found a sample difference of 33,000, right? So it's very possible that that is 23 standard deviations above 0, right? That's a value that's really far away from 0. Now, it's kind of hard. I can't envision this math like in my head, millions, and then dividing by saying I can't do that in my head. So it's a matter of just working through it, right? So once I plug everything in, I actually do in this example find a test statistic that's 23. But that's because the sample evidence we found was really extreme, right? So we're thinking about, once we turn this into a test statistic, approximately 23. It's pretty large. Okay? Now, if I was using the critical value approach, this one's pretty easy. Well, use a different color. If I plot my test statistic of 23, I mean, that is far into my rejection region. Right? This one's one where I can easily reject at the 99% level or the 1% significance level. Now, I could have also done the p-value approach. It's a little bit trickier, right? But I think it's good to kind of talk through it. So if I wanted the p-value approach, remember, I have a two-tailed test. So I could find the area to the right here, but every value I see here, it would have been equally as likely to see a value that far away on the other side of the distribution, and those values go against the null if it's a two-tailed test. Right? So I can find the area in this tail, but then I have to do what to find my p-value? Yeah, if I've got two tails the same size, multiply by 2. Okay? Or add it to itself, I guess, if that makes more sense to you.
Or like 2000.
Test statistic?
Yeah.
Are you forgetting the square root? Are you putting the actual zeros in for millions? You gotta put the zeros in, right? These are, I'm shorthanding, sorry. I'm shorthanding up here, right? So you should be 174,000. Yeah, go. Any other questions? And probably I won't be annoying like this on the exam and give you something with, but this is an interesting example because it's pretty relevant. I actually tried to go grab these values from some, from the AMA, the American Medical Association. So we've got this extreme test statistic, right? Clearly going to reject at the 99% level. If I want to do the p-value though, what's the area to the right of 23 going to be? It's going to be pretty close to. Pretty close to 0, right? If I look at this student T table, and I think the degrees of freedom I gave you was 80, right? We used. Well, the area to the right of 2.6 was 0.005. So the area to the right of 23 is going to be a lot of zeros and something, right? It's going to be really, really small. So if I've got approximately 0 times 2, well, that's still going to give me a p-value that's approximately 0. Right? Now, I might do something like this on the exam, where if I give you an example where there's an extremely large test statistic, one of the possible answers could be that your p-value is approximately 0, right? If it's past this last test statistic, right, that you can find in that t-table, any test statistic further than that, you're just getting closer and closer to 0. So if I've got a p-value pretty much 0, we said we only reject if that p-value, I'm talking and I'm writing, is less than alpha, okay? So if my p-value is less than alpha, I can reject. If I compare to my kind of 3 benchmark alphas here, well, approximately 0 is going to be less than anything, right? As long as I'm not using an alpha for like the 99.9999999% level or something like that, right? Our 3 benchmark alphas, that p-value will be less than all of them. Okay? So, you know, with this example, I could say, like, I found extreme evidence that there's a difference in male-female physician salaries. You know, from here, you know, hopefully we need to dive deeper, find some policy, what's happening, why is this occurring? Any questions over anything here? I want to do one thing here. I'm going to change the example a little bit. So let's say I found a test statistic of 1.8. So let's say I found this test statistic and it was 1.8. Well, I need to find the area to the right and multiply it by 2, just like we did before, right? So I go to my t-table, I look up my degrees of freedom of 80. 1.8 is not one of these values, but it is in between these two, right? So what I know from this table is, so 1.99 and then 1.664. The table lets me know, okay, the area to the right of those two values is 0.05 and 0.025. Right? So what can I say about the area to the right of my test statistic? It's going to be somewhere less than 0.05, but greater than 0.025. I can't say exactly using the table, but I can tell you that it's somewhere, actually here, let me write this out. Area to the right, it's going to be somewhere in between 0.025 and 0.05. So what can I say about my p-value? Well, if the area in that right tail is in this range, I have another tail on the other side of equal size, then it's just like we were doing before, we would just multiply both kind of bounds of our p-value by 2. So we could say here, my p-value is somewhere in between 0.1 and 0.05. Okay? So on the exam, if I give you a test statistic, I'll give you one of these exact values that you can look up. When it comes to the Connect assignment, it has some problems where it only gives you possibilities for the range of the p-value. Okay, and this is kind of how you would approach those. Any questions on that idea? Okay with that? Okay, so let's moving kind of quick. So if you have any questions, stop me anytime and just real quick. So this is an interesting example, right? Where we found this huge difference in physician salaries. But, if you start thinking about it, if you go back 40 years, it wasn't as easy for females to get into to become a physician, or you had fewer selecting. So you're going to have more males that have more experience. Possibly, they're selecting, men and women selecting to different types of medicine. And so there's all these other things that could be changing that we're not controlling for. So yeah, we found this difference, but can we actually say there's discrimination? Well, not technically, right? We'd have to control for all these other factors. And then if we see a difference, well, yeah, now that's a really powerful statement, right? If I've got two people with the same experience, working in the same medical field, like et cetera, same everything, same degrees, and I still find a difference, well, then that could be evidence of discrimination, right? So we want to kind of move towards this direction where we don't just want to look at the change or the difference between two groups. We want to be able to hold all these other factors constant. So the first step or the first look at this is going to be what we call matched pairs. And then we're going to transition to the next 2 weeks, the last 2 weeks of class, looking at what we call linear regression. Okay? So start with matched pairs today, right? So this is going to be, we're not going to be reinventing the wheel. We're going to be doing something that we basically already done. Okay. So all these other examples we've worked through since the exam and 2 population examples. With matched pairs, we technically only have 1 population, right? But we generally have 2 different time periods. And you can do it without time periods. In fact, the Excel example that we'll work through on Friday will have something other than time periods. But for the sake of the examples today, the ones that I often will use and the ones I'll use in the exam, it's generally that we look at matched pairs for time. Okay? So it's going to be this scenario where, let's say, we've got to head up here, I think. There you go. 10 workers, right? And I don't know, move my workstations around. I want to know, did my workers' productivity increase or decrease as a result of this thing that I changed? So I might have, what was their productivity before? And then I've got, what was their productivity after? Right? So what I'm going to do with matched pairs is what I'm really interested in is what is the mean difference, right? Or what was the average change in my worker productivity? It's a little bit different than saying what was the change in my productivity before and after, because now I'm saying what was the average change per worker, right? So what I'm going to do is create, based off of these other 2 productivity variables, this difference, right? So this person, their productivity went up by 3 units. Maybe this is like the number of sales they make in a month or something like that. This person, 2 fewer sales, 2 more, 5 more, etc. Okay? So I've now got this difference variable. If I'm interested in what was the average change or what was the average difference, it goes back to, I'm just going to find the sample mean of this variable I created. Okay, so we're just going to notate this a little bit differently, where I'm going to call this kind of difference between new productivity minus old productivity, or after minus before. Instead of the sample mean X bar, we're going to write this as D bar. Right? And all that's going to indicate is I calculated the sample mean of a variable that I created from two other variables. Okay, but it's the same 10 workers, right? It's just one, we still have one population. So we think about things like confidence intervals. This is how we found our confidence interval if we had a one population sample mean, or we only had a sample variance. When we're dealing with these mean difference variables, it's going to be exactly the same. It's just that the notation changes, right? To indicate that we're using the mean of this difference variable that we created. Okay? Other than that, everything's exactly the same. So these magic pairs examples should be easier, I think, than the two population stuff we've been doing, right? Because this just goes back to just a different notation for one sample mean examples. Okay? Any questions on this idea before we keep moving here? Okay, so, well, I already got it up here, but the other thing that we need for our student t-distributions is what? Degrees of freedom. Well, if I just got one population, how do we find degrees of freedom when we had one population? Degrees of freedom was simply, yeah, someone said it, n minus 1. So this goes back to the easy way to find degrees of freedom, okay? So, variable mean, so when you think it's over, the confidence interval strikes back. So I actually had a student make this one and send it to me. So if you ever have meme ideas and you want to make one for that, send it to me. I might use it in future classes, right? So we have this example, right? And we change the workstation or whatever, and we find that the average change in our workers' productivity was 8.5. We'll then plug in that sample variance we also found, which is 121. And we had 10 workers, so our sample size was 10. That comes from the previous slide. That's not, for whatever reason, I forgot to copy and paste that over. Okay. So the only thing left we need to do is say, okay, what number of standard deviations or what t-value would give me a total of alpha outside of my interval, which would mean that there's half of alpha on each side. If I want the 95% confidence interval, what's my alpha value? 0.05. Yeah, just 0.05. So 0.05 over 2, 0.025. My degrees of freedom is going to be what? My sample size is 10. Yeah, just 10 minus 1 or 9. Okay. So I go to that student t-table. I know that I want 0.025 in my tail, but I got to go way up here because my degrees of freedom is only 9. So 2.262, that's the last thing I need. Now it's just a matter of getting this entered into my calculator. Add that margin of error to my upper bound, subtract that margin of error to my lower bound. Okay. Any questions about how I found that t-value? Yeah. So that was from the very first slide where we had 10 workers. Yep. Yeah, if this was like a problem you were given on a homework question or something like that, it would, all be on the same slide. Yeah. Any other questions on this? Yeah. Yeah. So I'll come back to that. So if we plot what our confidence interval is here, I mean, we need to compute it. We need to have a way to compute these confidence intervals, but it's not like we're just calculating these for the sake of calculating them, right? It's once we have them, they tell us something. So here, if I was interested in the average change in worker productivity or that mean difference, right? And I come up with my confidence interval, what I'm saying is that true mean difference is somewhere in this range of values. So if I only have positive values here, what can I say with 95% confidence about my workers' productivity after this change? It's gone up, right? Now, if I only had, I don't know, -5 to -3, Well, now if I only have negative values in that range, I would say that, well, actually, this change made productivity go down or decrease. Right? So anytime you have a range of values that doesn't include zero, you can make a statement, right? You can say that this is either going up, this is going down. Now, let's say I wanted to make that same statement, but I want to do the 99% confidence, right? I want to say it with 99 instead of 95% confidence. What's the only thing that's going to change? Alpha value. So what's going to happen to alpha? So it's going to be smaller. What's going to happen to the number of standard deviations I need to go? It's going to be larger. If this is larger, what's happening in my confidence interval? It's going to be wider, right? If I have a larger value here, I'm adding and subtracting a larger margin of error. I'm going to end up with my upper and lower bound kind of going out even further. If I look at how close this is to zero, I can't do that math in my head, but if you work this one out, my guess is this goes to something like, I don't know, could even be like -1, right? It just kind of goes a little bit further out. Well, now at the 99% level, I can't say anything because the change could be positive, it could be negative, but it could be that there was no change at all, right? That zero is in that range, okay? Any other questions on that before we keep moving? Okay. Time. All right, I think we should be good. So we can also do hypothesis testing with this stuff. So we'll work through a hypothesis test real quick. So the test statistic equation, it's going to look exactly like what we were doing before with one population examples. It's just that instead of the sample mean, we're using that mean difference. And the variance isn't going to be the variance of a variable, it's the variance of our difference variable. But other than that, this is exactly what we had when we were looking at sample means. Okay? So I've now got this test statistic equation, and I'm going to be kind, and I'll give you an example today where I don't use this, but on the exam, right, I'm always going to use that assumed true difference of 0 here as well, right? Because it's kind of like the two population stuff. Like we want to know, did productivity go up? Did it go down? Or did it change, right? We're not usually saying, did it go up by X amount, right? Excuse me. So we have the same type of tests, all the same principles applied, nothing really new here, right? So let's go back to that example. And I said, okay, what's my test statistic for this productivity change example? So I've got my mean difference, right? Actually, let me skip ahead here. Okay, I'm going to make it up then. So let's say what I want to test for is, did worker productivity actually increase, right? That's what I'm trying to test for. So I'll assume the opposite is true, which is that it's actually decreased or didn't change at all. Okay? So here I'm going to be using this assumed true difference of 0, plug in my sample variance. Remember, we had 10 workers, our sample size. It's a matter of getting this entered into our calculator. In fact, it's going to be easier than what we were doing before because subtracting 0, I can essentially ignore that, right? If I'm always giving you this assumed true difference of 0, we always kind of ignore that part. So this is just a matter of getting those values plugged into your calculator correctly. What we do, we end up with this test statistic of 2.44. Any questions over this idea so far? So this should be, once again, these test statistic equations. From these test statistics, it's just a matter of you'll have the formula in front of you, just plugging the values in. More practice, working through these, trying to reproduce answers to make sure you can get these entered into your calculator correctly. Okay. So I found this test statistic of 2.44. Okay? I found something that was a certain number of standard deviations above that assumed true difference of 0, so I possibly could reject the null, right? But what levels can I reject that? So here's where we could very quickly find our critical values. The p-value approach, we're using that student t, so we'd likely have to put it in a range again. So if it was me, I'd probably use that critical value approach. So what would my degrees of freedom be if I had a sample size of 10? We said that was 9, right? N-1. if I then want to use my benchmark values of 0.1, 0.05, and 0.01, I've got 1.38, 1.83. What's the last one? 2.82. So I'll move out of the way here in a second. Usually it's better to plot my critical values and then plot my test statistic. I think it's just a little bit easier. But here, all I'm doing is, what were those three critical values, right? Degrees of freedom of 9, what gave me 0.1, 0.05, and 0.01 in the tail. Now, for a right-tailed test, that greater than sign an alternative hypothesis, the rejection region will be the area to the right. Okay? For left-tailed test, it would be the area to the left of my critical values. What's also going to be true about critical values for a right-tailed test? They will always be positive, right? If I'm looking at my student t-distribution, just like the standard normal, it's centered around 0. So I'm looking at the right side, positive values. Here, what levels could I reject at? Well, is my test statistic in the rejection region at the, for the 10% level? Yeah, so I can reject. What about the 5% level? Yep. What about the 1? No, right? It's not quite in the rejection region for that 1% level. Okay? So this critical value approach, I think, has this nice visual to where you can plot those critical values, that cutoff number of standard deviations. The area to the right is the rejection region. If the test statistic falls in that rejection region, you can reject at that level. If it doesn't, you fail to reject. Okay? So it's basically like saying, if I see something that's more than 1.83 standard deviations away, I'm okay rejecting what I assume to be true because it's far enough away that what I assumed probably is wrong, right? So in this case, we found something that was a little bit further away than that. Okay. Any other questions before you keep moving here? Okay. Trying to be a little more deliberate here. Oops. So I had an error in this one, or I changed this for the other class, so it should read like this. So these answers, let me see. Everything should be, I'm gonna go here and change this real quick. This should be -5.53, 1.33. Okay, so I'll change this on the updated version of this, or the complete version of the slides I post. So we can kind of ignore the possible answers here. I'm not using this as an actual question or anything. So let's say I have this situation where I'm looking at Starbucks card holders, and I want to know whether or not their calorie consumption has changed before and after calories were posted to the menu. So I've got the same 40 people, right? Same one population. I find that the average kind of difference for these 40 people is -2.1. I've got a variance of 64, right? Now I want to find the 99% confidence level. Okay? Well, all I do is start plugging in the things that I know. What was that variance? 64, 40 cardholders is my sample size. The only thing left I need is, well, what's my degrees of freedom? Well, if I've got a sample size of 40, just that -1 or 39. So I've got a sample size of degrees of freedom of 39, and I want to build a 99% confidence interval. So I need to find the t-value, or the number of standard deviations the way I need to go, to get a total of alpha outside the interval, or half of alpha on each side. So 0.01 over 2 is 0.005. So I'm going to go to my t-table. I wanted 0.005 in that tail. Degrees of freedom of 39. Am I in the right row? Yeah, 2.708. The last thing that I needed. Once again, now it's just a matter of getting this entered in my calculator. Add my margin of error to my upper bound, subtract my margin of error to my lower bound. Okay. Questions on that? Yeah.
What would that be a two-tailed test?
So we're not doing any type of hypothesis testing yet, right? This is just building my confidence interval. With confidence intervals, we always have two sides to our interval, right? So with confidence intervals, you're always dividing alpha by 2 when you're looking up the number of standard deviations away you want to go. These aren't critical values. This is just the number of standard deviations away you're going to build that confidence interval. And I'll make the connection here in a second between confidence intervals and hypothesis testing. So I'll mention it now though. So with confidence intervals, it's almost like a two-tailed test where you start out with no assumption about what side that statistic is going to be on of 0. With one-tailed tests, you're ruling out one side of the distribution, right? So it's actually like confidence interval and two-tailed test. That's probably the more appropriate approach, right? Because who knows, like you don't want to build your own biases in there. You want to assume that you could find sample evidence on either side, right? With a one-tailed test, we still have them though, because it's things like I don't inherently know. I mean, you'd have to look at some of the previous data, but like we know that if we look at data, male physicians on average earn way more. So we want to say, can we say there's an actual difference, right? We probably know what direction that difference is going to be. But confidence intervals and two-tailed tests, we don't assume anything about the direction. That's why we gotta have two sides there. Any other questions before we keep moving? It's a good question. So we actually work this out. We get something like this, right? So with 99% confidence, what can I say about calorie consumption, changing calorie consumption here? Yeah, could have positive, could have been, could have went up, could have went down. Could have mean that it didn't change at all, right? If 0 is in that confidence interval, one of the true differences could be that it didn't change, right? One of the true differences could be that it was 0. Okay. So, and also, I asked my last class, I was pleasantly surprised that most people know what movie this comes from. But if you haven't seen Napoleon Dynamite, all of you should. It's dry humor, but it's hilarious. So, we've got this confidence interval, and we said that 0 is one of the values in it. Could be the true difference. So if I do a hypothesis test where I assume that that difference is 0, what should be the outcome of that hypothesis test? If I'm saying 0 could be one of the possible values. If I assume that that difference is 0, I should be, if 0 could, so let's say, maybe having the visual will help, right? Let's say I assume that that difference is equal to 0. My confidence interval is telling me that could be one of the values. So if I do a hypothesis test for this, I should be two-tailed, but would I reject or fail to reject? If 0 could be one of the possible values, yeah, then no, I can't reject that the difference. The confidence interval is telling me 0 could be one of the possible values. So why would I be rejecting it, right? Now, it's two different approaches, right? Confidence intervals, I've got this range of possible values. My two-tailed test, I'm just ruling out individual values. But there's a little bit of advantage with a two-tailed or hypothesis test because having a p-value, I can compare like to a ton of different alphas simultaneously. Confidence intervals, I have to build for every single alpha. So there's advantages to doing a hypothesis test versus confidence intervals, but they're very closely related. If 0 is in my confidence interval, I should be failing to reject if I do a hypothesis test for that value of 0. So let's say we want to do a hypothesis test and we want to know whether or not calorie consumption has decreased, right? After posting these calories to the menu. So we find the sample difference of negative 2.1. And I want to know, did calorie consumption decrease? So what do I want to test for? Was that average change what? If I think that it's decreased, then the change would be negative, right? Which would mean my assumed true value is that change was greater than or equal to 0. So, I found a sample difference of negative 2.1. That goes against my null, so I might reject, right? Now we kind of already know, hopefully I shouldn't be at the 99% level, but I could be rejecting potentially. if I hadn't done this previous work with the confidence intervals. What type of tail test do I have? Left tail, right? Less than sign of my alternative hypothesis. So I've got this left tail test. Okay. From here, we want to do one of two approaches. So I need to turn this into a test statistic. I could then either look up the area to the left to find my p-value, or I could plot a critical value and see, is that test statistic in the rejection region? So what is my test statistic? Well, this is where I changed it for the other class too. I forgot to change it back. Sorry, I did something a little bit different with them, but I think this is better. So which of these test statistics should I be able to rule out right away? Positive ones. Why? If we're always using that assumed true difference of 0, I found sample evidence that was negative or on the left side of the distribution. I'm going to be a certain number of standard deviations below that assumed true difference. So right away, I know it's going to be C or A, right? From there, I just have to plug in my values, right? I've got negative 2.1, assumed true difference of 0, 64. And if we go back, it's not on this slide, but 40 card holders, right? So our sample size is 40. Excuse me. So I get this test statistic of 1.66. Okay. If I tried to find the p-value, my degrees of freedom would be 39, right? Sample size minus 1. So I go down here, 39, and I look this up. Well, I don't have exactly 1.66. So once again, I can only put my p-value in a range here. So it's just the area in this left tail, right? So 1.66 would be in between these two test statistics. So the area of my test statistic to the left of my test statistic is going to be somewhere in between 0.1 and 0.05. Right? If you're struggling with that concept, the idea is like, if I have a test statistic and I can't find it here, I just find what it's in between, and my p-value will then be in between whatever areas to the right of those two. So the area to the right of 1.3 and 1.68 is 0.05 and 0.1. So the area to the right of 1.66 is going to be somewhere in between that, right? So what levels here can I reject that? Yeah, my p-value, right? We only reject if the p-value is less than alpha. So for my alpha of 0.1, my p-value, it's in there. It's going to be less than that. Is it going to be less than 0.05? Well, this is telling me, no, the p-value is greater than 0.05. So I could reject at that 10% for the significance level or 90% confidence, but I'd fail to reject at the 5 and the 1% significance level, or I'd fail to reject with 95, 99% confidence. Okay. Any questions on that before we keep going here? Okay. So what was my rejection decision at the 99% level? Well, alpha be 0.1, I failed to reject, which, so my confidence interval let me know too. Now, what I've said is technically a little bit wrong, but I say it to get the principle instilled. If 0 is in your confidence interval, you still could reject it using your hypothesis test if you're doing a one-tail test. Anytime you're doing a two-tail test, it starts out, this was a good question earlier, it starts out with the same assumption that I don't know what side of the distribution this difference should be on. And so if you have 0 in your confidence interval for a two-tail test, you'll always fail to reject it. It's possible, not very likely, but it is possible for a one-tail test, it could be in your confidence interval and you actually reject it. But that's because you've switched to only looking at evidence on one side. That was not your natural assumption when you were building confidence intervals. Okay. So one more thing. So we've got the critical value approach we could have also used, right? So if I've got my degrees of freedom of 39, and I want my benchmark kind of 0.1, 0.05, and 0.01, I've got what? 1.304, 1.685, and 2.423. What did I do wrong here? I erased the null. But remember, what did we start out with? We had a left tail test. So these are going to be my critical values that give me an alpha of 0.1, 0.05, and 0.01 in my tail. But what else do I need to do? The left tail test, my critical value should always be negative. So it's going to be these same values, because remember the student T table looks at the area to the right. Oh, well, it's going to be these same three values, but negative. So negative 1.304, negative 1.685, negative 2.426, right? And I think about, here's my rejection region now, the area to the left, right? My test statistic is in my rejection region at the 10% significance level. So I reject there, but it's not for the 5 and 1%, which is the exact same thing we said using the p-value approach. Okay? So two ways of determining rejection. And actually I wrote 1.66 here. Sorry. That was negative 1.66, right? When we plug those values in, because we had that negative sample difference. So you can find the values using that student T table for your critical values, but you have to remember that if I have a left tail test, it's those values, but negative. Questions here? Yeah.
So like once you find the test statistic,
Mm-hmm.
and you know that it's negative,
Mm-hmm.
can you just take like that with the value and like
If you wanted to, if that's, yeah, I don't usually say that just because it's like another step and I don't want to confuse anybody. But yeah, if you wanted to, really what we're doing here. So if we write it out mathematically, regardless of whether or not it's a left or a right tail test, this is how we're making our rejection decision. We're not looking at, we're just looking at the magnitude, right? If my test statistic is more extreme than my critical value or larger in absolute value, right? Because this is actually a smaller number, it's a larger negative value. So if it's easier for you, yeah, just be like, well, I'm just going to make all these positive, and then everything still should be true, right? My test statistic will be in my rejection region at these same levels. I'm just basically flipping it over here so I don't have to deal with negative values. Yeah. Any other questions on that? All right, so this should be everything you need. This matched pair stuff is everything to get through that entire Connect assignment. That's due at the end of the day next Wednesday. So if you haven't started it, I would highly suggest getting going on that. Get that out of the way early, because that next, that Excel assignment after Friday's class, you'll be able to tackle the entire Excel assignment. We'll work through sample means when we have sample variances. We'll work through match pairs and work through sample proportion examples all in Excel on Friday. Okay. Yeah.
After this Connect Excel, we have another one after that as well.
Yep. So there's going to be 5 Connect total, 5 Excel total. So they will be kind of running through. But if you've done the first 4, like I mentioned, yeah.
Are you dropping cells?
Yep. So 4 Connect assignments will count towards your grade. 4 Excel assignments. So I'm dropping 1 at each time. And then also I'm dropping 3 of your lowest items. Now, none of that gets reflected until like finals week, basically, or on Monday, I'll have everything updated, and I'll give you also, that's not out there yet, but I'll give you this kind of figure out your grade calculator, so you'll have you'll know exactly where you stand in all these different categories, and you can play around with the final exam grade to see, okay, if I got this in the class or in the final, what would I get in the class? If I got this grade on the final, what would what would my grade be in the class? But that's something that I'll pull up, show you in class as we get closer to the exam. Okay.
Are you posting the last Excel next, like the week of finals week, or
No, I'll be putting them up early next week. Yeah, I'll put them up on probably after class Monday, so you can start chipping away as we kind of cover stuff. Any other questions for me? Okay. All right, enjoy this weather, and I'll see you guys on Friday.